In today's lesson, we are going to be looking at some special triangles. So in the previous lessons, we've calculated side lengths, we've calculated angles using the trig ratios and sine and cosine law, but technically those have been estimated decimal values. Right? We've had to round in certain scenarios, or we've rounded our final answer, or because it's been a decimal, it's gone on forever. So that decimal, even though our calculator only showed us maybe 10 decimal places or however many decimal places it can hold, there might be more values after that. So we've really been estimating the exact length. For our purposes, it's been fine, but when you get into more specialized fields, you might say, where the calculations are very necessary, whether you're designing something, you're projecting something, you're kind of running experiments or models, and you need it down to an exact value, we might need those. We might not be able to use the estimated values. Now, when we're dealing with coming up with the exact values for these ratios or these side lengths or angles, whatever the case may be, there are two special triangles that we can use that either they sometimes come up often or they just happen to have very kind of like unique measurements. So there's two special triangles we're going to be dealing with. They're again both going to be right angle triangles. The first one is going to be an isosceles triangle where we have 90 of our right angle and 45 degrees as our two other angles. And in this case, because we have an isosceles triangle with the two angles being the same, the two side lengths are also going to be the same. In this case, they're both 1. So 1 and 1. And then using sum of squares or Pythagorean theorem, that would give us a hypotenuse of the square root of 2. So for this triangle, this is when we have a 90-degree angle and two 45-degree angles on the other side, these are what the dimensions are going to be. Now you could have, we talked about similar triangles before where it keeps the same angle, but maybe the measurements are magnified or they're doubled, so to speak, or things like that. So you could potentially change some of these side lengths. The other triangle, it's going to be when one angle is 30 and the other angle is 60. So you have a 90-degree angle, a 30-degree, and a 60-degree. And in this case, we have 1 and root 3 as the two legs or side lengths, and our hypotenuse will have an exact measurement of 2. So these are the two special triangles that you may come across. If you think about an isosceles triangle with both 45, just in terms of visual appeal, things like that, that tends to be an appealing looking triangle. Same with 30 and 60, the relationship between the angles. You can kind of see where that might come up into play in certain things. So we can use those exact values to determine what the exact trig ratios would be for the different angles. So sine of 45, so if we look at our 45-degree angle, it doesn't matter which one, you can pick one. Sine, remember, is opposite over hypotenuse. So either way, our opposite is going to be 1 over the hypotenuse of root 2. For sine of 30, if we go to our second triangle, use 30 as our reference angle, opposite over hypotenuse. In this case, it's 1 over 2. Sine of 60, so sine of 60 degrees, again, opposite over hypotenuse, so root 3 over 2. So all we're doing is using the angles in these special triangles to help us figure out what the sine of certain angles would be. Usually they're common angles like the 45, the 30, and the 60. For cosine, it's going to be the same idea. Look at 45. So cosine is adjacent over hypotenuse. So in this case, 1 over root 2. So again, same thing as the sine of 45. For cosine of 30, again, look at our special triangle with the 30 degrees. Adjacent over hypotenuse. So adjacent is root 3 over hypotenuse, which is 2. For cosine of 60, same idea, adjacent over hypotenuse. If we look at our special triangle, it would be 1/2. And then for tan, again, same thing that we've been doing with the other ratios, except tan, remember, is opposite over adjacent. Let's actually just go back and say O/H, A/H, and O/A. So opposite over adjacent is 1/1 for 45 degrees, or just 1. For 30, opposite is 1 over adjacent, which is √3. For 60 degrees, opposite is √3 over 1, or just √3. So now, if we're ever asked to find what is the ratio, or what is sine of 45, or cosine of 30, or tan of 60, we can now give an exact value. We don't need to punch it into our calculator. We might need to memorize these to do it, but we can give an exact value. So we're going to be using that idea to find out what some of the exact values are going to be, or given some of these ratios, determine what our angle might be. So for example, we want to use the special triangles to work backwards and determine the angle. So if we have cosine of theta is equal to √3/2. So √3/2 is our A/H, or adjacent over hypotenuse. So we can go back to our table, find where we see √3/2 for cosine. We see that it would be when the angle is 30. For tan of theta, or tan of an angle, equals √3. Again, tan is opposite over adjacent. We're going to go back to our table, go to tan, and see where do we see √3. Well, we see it at 60. So that means that our angle is going to be 60 when the ratio is √3. Sine of an angle is 1/√2. Sine is opposite over hypotenuse. We can go back to our table, find where we see 1/√2. In this case, it's at 45 degrees. So therefore, when our ratio for sine is 1/√2, our angle is going to be 45 degrees. So really, that's all we're doing. We're just looking for a certain combination of specific side lengths to then help us figure out the angles, right? So it only works for certain angles and certain measurements. That's why they're called the special triangles. Now, we can find exact values in other scenarios as well. We can use that by leaving the side lengths in radical form. So by not even going through and doing the final calculation, just leaving the ratio in its form. So if sine A is equal to 8/13, we want to determine the exact value for what tan B would be. So let's just first label our sides. We're not going to be referring to the right angle except to label the hypotenuse, so we can just label A and B. So if sine of A is 8/13, sine is opposite over hypotenuse. So that means if this is my angle A, opposite is 8, hypotenuse is 13, and we have one unknown side. In order to find tan of angle B, we do need to figure out that missing side, because remember, tan is opposite over adjacent. We have the adjacent, we don't have the opposite. So how do we find that missing side? Well, we can find a missing side in a right angle triangle by using the sum of squares, or Pythagorean theorem, which is 13, let's start from the original one. A squared plus B squared equals C squared. A and B are your legs, so 8 squared plus, we'll say, B squared is equal to 13 squared. We'll go through and solve. We get 64 plus B squared equals 169. Move the 64 over. Get B squared equals 105. And B would then equal the square root of 105. Now, in this case, we are not going to find what this exact value, we're not going to find what this value is. We're not going to plug in the square root of 105 into our calculator. Unless it gives us an exact nice answer, meaning that b is a perfect square, which in this case it would not be, we're just going to leave it as the radical or the square root form. So that means that I can now say that this side length is root 105. And that's what I'm going to use in my calculation. So then, for the next step, the actual answer, tan of b, which is opposite over adjacent, is root 105 over 8. And that's what I'm going to leave as my final answer, because that is the exact value. I'm using the radical or square root form, and that is the exact value of tan b. For the next one, same idea. We're going to label our two sides. Say a and b. Again, it doesn't really matter. We can swap it around if we wanted to. It doesn't really matter as long as we label the sides correctly based on what we're given. So we're given that cosine A is equal to 3 over 7, and we want to find the exact value for sine A. Well, if cosine A is 3 over 7, I have my reference angle A. Cosine is adjacent over hypotenuse. So that means 7 is the hypotenuse, 3 is the adjacent, and we don't know what our missing or our third side is. Similar to the last one though, we can use the sum of squares to find that missing one. So again, a squared plus b squared equals c squared. 3 squared plus, say, b squared equals 7 squared. 9 plus b squared equals 49. Move the 9 over, we get b squared equals 40. And we can simplify that to b equals 40, or the square root of 40. Again, square root of 40 doesn't give us a nice answer, so we're not going to evaluate it any further. We're going to leave it as that. So now we can go back, put root 40. Now we can go back and find the exact value for sine of A, which is opposite over hypotenuse. We now have our opposite, which is root 40, over our hypotenuse, which is 7. So sine A is equal to root 40 over 7, and that is the exact value. We can estimate it by actually going through and doing the calculation, but we're just estimating at this point. So again, the main idea is from this lesson is, one, recognizing that there are special triangles when we have a certain arrangement of angles. They do give us a certain triangle with predetermined or specific or exact side lengths. And we can basically look and see the different combinations for sine, cos, and tan for those side lengths, that if we do see them, it should help us figure out exactly what the angle is. So it kind of saves us on going through the calculations. It's kind of like a shortcut, you might say. And then we can use that to kind of work backwards, as well as finding the exact values for other triangles, even if they aren't necessarily considered special triangles. Right? So we might not be able to work backwards and figure out the exact angle, but at least we can figure out the exact value or exact ratio for each of those for any side length. So again, just kind of a different form of looking at finding values or finding these measurements, and just being a little bit more specific, because in some scenarios it may be required that we are very specific and exact in our measurements or calculations.